unless it's some sort of arithmetic trick. But let's get to like by strict definition. Okay, so 4. 4. How many factors does 4 have? It has 1, 2, and 4. That's all the factors of 4. So we'll say D of 4. What if there is some sort of pattern to this? So now we know the number of factors is 3. So we can write in the cardinality of D4 equals 3. So has 3 factors. And note that this is the notation for cardinality of a set. So on this, let us discuss, is there a pattern to count these guys? As you notice, this looks like it might have some sort of pattern if you're clever to think about it. If you notice the pattern with the prime numbers, you notice that they're unique in some sense. And that if you multiply them together, you get back to the original integer. Because they all divide that integer. So, let's think about it this way. Suppose we're given some sort of prime number. Say we'll just call it P. And it's raised to some S. P raised to the power of S. So this is P times P times P. P, this is S times. It does it S times, which is equivalent to saying size 1 of P. This is basically your product notation. So if you've ever seen summations, this is equivalent to the product version of that versus the sum of things. So each element in here is multiplied instead of being added. So this is equivalent to this guy up here. So, how many factors does this guy have? Wouldn't you agree that this has P? It should have P squared, P cubed. Whoops, not addition. It should have P to the 4, P to the 5, all the way to P to the S. And also it should also include P to the 0, which is equivalent to 1. Because all these guys are unique, you can write them as a product, get back to this number. And now notice here, how many of these guys do we have? We have, let's see, we have S here, then we have this extra one. So there's S plus 1. Different factors for this prime number. What do we know about things like this, then? Since we can write it out in this fashion and can get a discrete value. Discrete as it's not continuous. And it's very easy to compute, in some sense. This is probably some sort of logarithmic computation. Just this specific example. I don't want to say a general case, okay? So, on this case, so we have something going on here. So we have P to the S. So the D of P to the S is, let's lower that down, P to the S is in fact S plus 1, as you've seen below. If you want a proof on this, I can easily provide it. Or I can give you a nice reference to a book that'll definitely give you the nice proof for it. Okay, so our number of divisors is S plus 1. 4, a prime number raised to some power. But what about just a prime number? As we just discussed earlier, by definition, D of P is 2. So now we've isolated every case involving prime numbers. As you can observe, we have these two conditions. So we have 1 and 2. But what useful property can we apply this to get some sort of useful result? Now look at this. Keep those two formulas in mind. Actually, I'll call them relationships rather than formulas. Formulas is a horrible word. Let's talk about relationships, because this is the natural relationship between prime numbers and the factors. Okay, so now on this, let us look at one detail which will be very important. We're going to be going to multiplicative functions. This is a multiplicative function by definition is the following. F of n, m, n times n, is equal to f of m times f of n. So we have this guy here. So if we multiply f of n and f of n, we should be able to get back f m times n. On this note, based on a nice proof, you'll be able to apply this property, in fact, to something we're going to define as the d function. The d function is multiplicative, sorry. So now we're going to define what the d function is. It'll pick all these concepts back together. Okay, d function. The d function, by definition, for some n, so other books like to use tau of n or d of n. One of these two is usually a good convention. So if you ever see tau of n, it's the same thing as d of n, unless it's defined otherwise, then I'm going to. Okay, so where d divides n, and we'll say 1. So this is a summation, so this is the number of divisors that divide n of 1. So we go, like in our example of 4. 1 divides 4, 2 divides 4, and 4 divides 4. And so if you add these up, you get 3. By definition, this is the d function, but here is a nice, useful theorem. A nice, useful theorem. Basically, we have ourselves d function d of n is multiplicative. I apologize for my writing, it's very ugly. Okay, so d function, d of n is multiplicative. This means now that if, say, we're given some arbitrary n for d of n, we can break it into, say, d of k, d of m. Can you see some sort of relationship between n, unique factorization theorem, and this multiplicative composition here? Let me just show you, maybe give you a hint of what's going to go on here. Given some fixed integer, say, let's give it 18. You know 18, as we described, is to the power of 3 times, no, sorry, 3 squared. And I may have made an arithmetic error earlier, so I apologize. So, times 2 gives you 18. And just for the sake of ordering, let's just, and note that this is unique based on the unique factorization theorem.